With 5 production lines operating simultaneously, will annual output truly exceed 300 aircraft? As foreign media buzzes about China's 5th-generation fighter production capacity, how much of this is grounded in reality, and how much is merely wishful thinking from those far removed from the production front lines? In recent days, a report by the Asian military website, Security and Defense, has continued to generate buzz within the industry. The article's core assertion is that the annual production capacity of the J-20 and J-35 is expected to reach the 300-unit threshold. This figure has quickly ignited heated discussions across military forums, with supporters viewing it as the inevitable result of the industrial system's long-term accumulation of capabilities, while skeptics argue that it defies the fundamental laws of high-end equipment manufacturing. Simply taking sides based on emotion serves little purpose. What truly needs to be done is to focus on the hardware infrastructure of the two major aircraft manufacturers, the actual state of their supply chains, and the unique production rhythms of the aviation industry. Starting with the hardware level, the infrastructure expansion of Chengdu Aircraft Industry Group and Shenyang Aircraft Corporation in recent years is indeed clearly visible. Since 2021, CIG has undertaken large-scale capacity expansion centered on the J-20 production system, with newly constructed facilities specifically designed to accommodate pulsed production lines. This production model, through assembly line-style workstation rotation, has significantly shortened the final assembly cycle for each fighter, with the J-20A and J-20S models now fully equipped with WS-15 engines. The power plant bottleneck that previously constrained mass production has been largely resolved. Having shed its reliance on external core components, large-scale production has entered a relatively stable phase. Currently, it is widely reported that Chengdu Aircraft Industry Group's 5 pulsed production lines are operating at full capacity, with an annual production capacity exceeding 100 aircraft under normal production schedules. If pushed to maximum capacity, a figure approaching 120 aircraft is not entirely out of the question. The integrated production base built by Shenyang Aircraft Corporation for the J-35 represents another crucial foundation for production capacity. The final assembly plant, spanning hundreds of thousands of square meters, is directly connected to a dedicated test runway. This eliminates the need for cross-area transportation from component assembly and final aircraft assembly to factory test flights. This highly centralized layout directly shortens the production cycle. Once the new base is fully operational, the J-35's production capacity will double compared to earlier stages, making it the second 5th-generation fighter to enter mass production. It will simultaneously meet the deployment requirements for both naval carrier-based variants and medium-sized stealth fighters for the Air Force. Based on this expansion of production capacity, foreign media outlets have presented a seemingly rigorous projection, combining the current production capacities of Chengdu Aircraft Industry Group and Shenyang Aircraft Corporation. Annual output could reach over 200 units under normal conditions. However, if production lines for 4.5-generation fighters are fully converted to 5th-generation models, and the massive demand gap is factored in, maximum annual production capacity could even reach the 300-400 unit range. This projection is supported by two key factors. First is the logic of production capacity substitution. Shenyang Aircraft Corporation has long been responsible for the production of the J-16 and J-15. As these two 4.5-generation fighters are now entering the final stages of production, their existing mature production lines, supporting supply chains, and skilled technical teams can be directly transferred to the mass production of the J-35, eliminating the need to build a production system from scratch. Second is the pressure from the demand side. A large number of early deployed models in the Air Force, such as the J-10 and J-11, are due for replacement. The commissioning of the Navy's new aircraft carrier also requires supporting stealth fighter jets, coupled with the expressed interest in 5th-generation fighters from certain overseas markets. The combined domestic and international demand suggests that large-scale production capacity could indeed be successfully absorbed. However, the issue lies in the fact that high-end equipment manufacturing is never simply a matter of adding production capacity. Even if the final assembly lines are capable of operating at full capacity, the ability of the supply chain to keep pace is the key factor determining the final number of aircraft rolled off the production line. The first major constraint comes from the high-end supply chain. The core components of 5th-generation fighters, including stealth coating materials, transmit, receive modules for active phased array radars, and core processors for integrated avionics systems, involve complex manufacturing processes and stringent testing standards, with production cycles far exceeding those of ordinary components. More critically, The WS-15 and WS-19 advanced aircraft engines are currently still in the ramp-up phase. The stability of engine mass production depends on the maturity of materials and processes, as well as the sustained improvement of yield rates, a process that cannot be accelerated simply by adding equipment or extending working hours. Even if the final assembly line maintains high-volume operations, the final production output will be severely constrained if the engine delivery schedule cannot keep pace. The second soft bottleneck lies in the technical workforce. The requirements for skilled workers and on-site engineers on a pulsed production line differ fundamentally from those of traditional assembly methods. It takes years of systematic training and hands-on project experience to go from mastering operating procedures to developing consistent quality control capabilities. While factory construction can be completed within 2 to 3 years, the training cycle for a mature final assembly and debugging team is far longer. Rapidly expanding production capacity on a large scale will inevitably lead to the risk of quality fluctuations caused by a dilution of technical expertise. The third constraint stems from the pace at which the supporting infrastructure of the equipment system develops. The combat effectiveness of modern air power has never been determined solely by the number of aircraft delivered. A pilot capable of flying a fifth-generation fighter requires extensive conversion training. Ground support teams must simultaneously familiarize themselves with the new model's operational and maintenance procedures. A spare parts inventory system must be established, and even airport hangars, refueling facilities, and munitions loading equipment require targeted modifications. If the pace of aircraft delivery far outstrips the development of supporting infrastructure, not only will combat readiness fail to materialize quickly, but it will also lead to resource misallocation and increased logistical strain. Considering hardware capabilities, the current state of the supply chain, industrial norms, and development timelines, a reasonable annual production capacity for the region's two fifth-generation fighters is more realistically estimated to stabilize between 150 and 200 units. Although this figure lacks the impact of the 300 aircraft projection made by foreign media on a global scale, it would firmly secure the top spot in annual fifth-generation fighter deliveries, far exceeding the actual annual production of the F-35, and would be sufficient to support the modernization pace of naval and Air Force aviation units, as well as national defense requirements. If this pace continues, the total number of fifth-generation fighters in service over the next 5 to 10 years will indeed lay the foundation for surpassing existing first-class air forces, and a realignment of the regional air power landscape is a foreseeable outcome. More importantly, the entire production capacity strategy is anchored in striking a balance between defense requirements and industrial principles. While advancing the mass production of fifth-generation fighters, technical resources are simultaneously being redirected toward sixth-generation fighter R&D, balancing immediate combat capability enhancements with long-term technological breakthroughs. This approach ensures that production planning does not blindly pursue extreme figures, but instead follows a sustainable path of capacity expansion, one that prioritizes supply chain stability, a robust talent pool, and coordinated support systems. The annual production target of 300 aircraft, which has been widely discussed in foreign media, is valuable as a perspective for observing the expansion of the region's aviation industry. However, equating this figure directly with an imminent reality would likely underestimate the invisible constraints inherent in high-end equipment manufacturing.